Welcome to the Explainer. Today, we're taking a visual journey through a classic physics mystery. We're going to decode those invisible forces that govern motion and really turn all that abstract math into physical reality. Let's get right into it. So here's the fundamental question that's hooking our entire investigation today. How do we mathematically predict the exact movement of a sliding object? I mean, it sounds simple, right? A block just goes down a hill. But to accurately predict where that block is going to be at any given second, well, that requires us to translate physical reality into mathematical certainty. So let's unravel this case together. Okay, let's dive into this. Here is our roadmap for today. First up, the sliding block challenge. Second, mapping the hidden forces. Third, applying Newton's laws. Fourth, solving for acceleration. And finally, predicting future motion. Section 1. The sliding block challenge. Setting the stage. So, our foundational problem reads like this. A block of mass m slides without friction down a fixed inclined plane, which makes an angle theta with the horizontal. Calculate the acceleration of the block. Now, I know mass m and angle theta sound super abstract, but remember, they represent a real, tangible physical object moving through space. Just imagine a sleek block of ice sliding down a perfectly smooth ramp. Our mission here is to figure out exactly how fast it's speeding up. All right, Section 2, mapping the hidden forces, the scene of the crime. Just notice the contrast here. On the left, we've got this messy, hand-drawn sketch, complete with scribbled-out mistakes and red ink. And on the right, the pristine, polished textbook diagram of the exact same problem. When you're mapping out physics problems, your initial notes might look totally chaotic. But the core physics concepts, the block, the angle theta, the arrows pointing in different directions, they are exactly the same in both. The underlying truth honestly doesn't care how neat your handwriting is.
Both of those images represent a free body diagram. Now, we already know this is the standard visual tool used to map all vector forces acting on a single object. But the key takeaway here isn't just reciting the definition. It's understanding why this is our absolute critical first step. We literally cannot touch the math until we isolate this object from the rest of the universe and clearly define every single push and pull acting directly on it.
Section 3. Applying Newton's laws. Making sense of the evidence.
Okay, step 1, identify gravity, which we write as capital M times little g. Step 2, identify the normal force, which is pushing perpendicular to the surface. And step 3, resolve these forces into their x and y components. Actually, because the block is moving down a tilted ramp, the math becomes infinitely easier if we just tilt our x and y axes to match the ramp itself. It's a real game changer. Now, what's really interesting about this slide is how the textbook neatly separates reality into two distinct lanes once those axes are tilted. On one hand, we've got our x-direction forces moving right along the plane. Here, the force equals mass times acceleration, written here as mx double dot, which equals mg sine theta. Then, completely separately, we have our y-direction forces acting perpendicular to the ramp. For this one, the force equals the normal force minus mg cosine theta. So by dividing the whole problem into x and y, this complex mystery is instantly distilled into two simple, totally solvable equations.
Moving on to Section 4. Solving for acceleration. Closing in.
Let's look at the y-axis first. Think about the physical reality of our block for a second. Is it magically levitating off the ramp? No. Is it sinking like quicksand into the ramp? Also no, because there's zero motion up or down relative to the surface. The acceleration in the y direction, y double dot, is exactly zero. This means the forces pushing up and the ones pulling down perfectly balance each other out. Therefore, the normal force, n, exactly equals mg cosine theta. Boom! The y-axis is completely neutralized. But the critical action is really happening on the x-axis. The force down the ramp is mass times acceleration, mx double dot. And that equals the gravity pulling it down the ramp, mg sine theta. But notice what happens next. We have a capital M on both sides of the equation. They cancel each other out entirely. We're left with simply acceleration equals g sine theta. So the crucial point is this incredibly profound truth. The mass of the block literally doesn't matter. Whether it's a tiny ice cube or a massive glacier on a frictionless incline, they are going to accelerate at the exact same rate. How cool is that? Finally, Section 5, predicting future motion, the math time machine. Just follow the mathematical progression here. We start with our acceleration x double dot equals g sine theta.
And this brilliantly illustrates how, through mathematical integration, we can step up to velocity x single dot by multiplying by time t and adding an initial velocity constant v0. Then we integrate one more time to find the exact position x. It becomes g sine theta times t squared over 2 plus v0 times t plus our starting position x0. Guys, we've essentially just built a mathematical time machine.
Now, to make this time machine actually useful, we just apply our initial conditions. Let's say our block starts at a dead standstill. At time t equals 0, our initial velocity is 0, and our initial position is 0. When those zeros are plugged into our big equation, all those extra constants just vanish. The math cleans up beautifully, leaving us with this neat final verdict. The position x at any given time equals g sine theta times t squared divided by 2. You just give me a time, and I can tell you exactly where that block is on the ramp. Case closed.
So we've successfully modeled a perfect frictionless world, but it begs a really fascinating question to leave you with. What happens to all our elegant, perfectly balanced equations when we add the messy, real-world force of friction back in? How does that alter a free body diagram? And more importantly, will the mass of the block still cancel out? I want you to chew on that as you continue your physics journey. Thank you so much for joining me on this explainer today. Keep learning, and I'll see you next time.